In problem 2.16, we are told that when a charged particle in a one-dimensional particle in a box absorbs or emits a photon, the quantum number n must change by an odd integer to be plus or minus 1, plus or minus 3, 5, 7, and so on. Transitions where n changes by an even number, like these transitions are forbidden. They're not allowed for the particle in one-dimensional box. We are asked to show that the allowed transition frequencies have the form nu equals k times h over 8ml squared. This is something we need to show where k takes on whole number values. The next thing we need to do is find the smallest value of k for which two different delta n values give the same emission frequency. So let's revisit that once we show that this is true. Okay, so given that the changes in delta n that are allowed are when delta n changes by plus or minus 1, 3, 5, any odd number. We know that this is the case. Given this, we can write delta E to be equal to maybe delta E when the state change is something like n plus 1 to n, let's say, where delta n is equal to plus or minus 1. We're just considering the case where it's equal to 1. In any way, in this case, it's going to be n plus 1 whole square minus n squared times 8 square over 8ml square. Right, so this I can write as once the n square and the, I can write this as n squared plus 2n plus 1. So this and this gets cancelled, right? They get cancelled, so I can write it as 2n plus 1 times 8 squared over 8ml squared. Now for delta n equals plus or minus 3, and n squared gets cancelled. I can take the 3 to be common outside, right? So this is going to give me now doing a similar thing for this. This will give me now by induction, when delta n is equal to plus or minus k, where k is an odd number, I can write this to be I mean, I don't have to derive it if it's by induction. I can just write using what we've seen before, but anyway. So this can be written as k squared plus 2kn times 8 squared over 8n whole squared. Now, this transition corresponds, transition of a photon corresponding to frequency nu. The energy can be written in terms of that as E, the delta E to be equal to h nu. So that implies h nu is going to be k squared plus 2kn. I'm going to cross out an h because that's common. So we show that v equals k squared plus 2kn times h over 8n whole squared. Right? And in the question, we are given that we need to show v equals k times h over 8n whole squared. And we showed exactly that, except that the k given here is equal to this term. I mean, we can change the k to any other variable. So I'm just going to write maybe I don't know, y squared plus 2yn. That looks odd, but. And this is definitely a whole number because this y itself is a natural number. So y squared also is going to be a natural number. And n is also a natural number. So yn is going to be a natural number and 2yn is going to be a natural number. And the sum of all of this would still be a natural number. That is definitely a whole number, right? So yeah, we have showed, we have shown the first part, which is the form of the frequency. Now let's move on to the second part. Find the smallest value of k for which two different delta n values give the same emission frequency. Okay, so let's write down what happens when delta n equals plus or minus 1. Right, when that happens, we know that the value of k would be something like, would be 2n plus 1. Right, so the frequencies are of the form 2n plus 1 times h over 8n squared. So this part is common, so I'm just going to ignore that. And I'm only going to write about this, the 2n plus 1 term. And if the upper level, if n plus 1 can only start at 2, the lowest n would be 1. So the upper level can be 2, 3, 4, and so on. The lower level can be 1, 2, 3, 4, 5, 6, and so on. Right? So this 2n plus 1 term can be 2 times 1 plus 1 could be 3, or 5, 7, 9, 11, 15, 15, 17, 19, 21, 23, 25, and so on. Now, when delta n equals plus or minus 3, k would be equal to 6n plus 9, right? So if you have y equals 3, that will give you k to be equal to 6n plus 9. So when you have this, the frequency terms will have will be of the form I'm going to ignore this part and I'm only going to care about that. So again, the lower values will always be 1, 2, 3, 4, 5, and so on. And the upper values can be 4, 5, 6, 7, 8, and so on, and higher and lower. So this term here would be 6 plus 9, 15, or 6 twos are 12, plus 9, 21. And 33, 39, 45, 51, 57, and so on. Now when delta n equals plus or minus 1, given that the lower value can start from 1, we can have this be 25 plus 10, 35, 45, 55, 65, 75, 85. And so on. Now let's see if any of the k values that we have written here, so these are the possible k values, right? So let's see if there are any similarities in any of the k values that correspond to delta n equals plus or minus 3, plus or minus 1, plus or minus 5. So maybe let's start with this 35, 45, 55. Well, there is 45 here and there's a 45 here. So we don't have a 35 anywhere here or anywhere here. So 45 is the lowest k between 5 and 3. Now let's compare if there's anything between 3 and 1, right? So between 3 and 1, we have 15 and we have 15 here, right? We don't have 15 here, but the first value of k, the smallest value of k here is there in both when delta n equals plus or minus 3 and also when it's equal to plus or minus 1. So the smallest value of k is 15. That corresponds to these two transitions. And the transition which the delta n plus or minus 1, the transition which gives a value of 15 is when you go from 1, 2, 3, 4, 5, 6, 7. So when you go from n is equal to 7 to n is equal to 8. That's when you see, that's when you get k equals 15. And the other transition that gives you k equals 15, where the delta n is plus or minus 3, is where you go from n equals to 1 to n is equal to 4. So k equals 15 is the answer, and these are the transitions that result in k equals 15.